Hi everyone, the topic of our group is integer factorization, which purpose is to factor a large integer into the product of several prime numbers. The large integer factorization is not only the most direct attacking method against RSA encryption, but also the most important point to analyze the security of RSA. That's the reason we chose this topic. We will introduce some model popular integer factorization algorithms. The first algorithm we want to introduce is ECM algorithm. ECM is considered a special purpose factoring algorithm. It's most suitable for finding small factors. As we all know, the greatest common divisor of n and some other values turn out to find a proper non-trivial divisor of n. And finding GCD by Eglandine algorithms is extremely fast, even among very large numbers. Eglandine algorithms also used to find multiplicative inverse mode n. This method utilizes this property. It computes a large multiple Kp of these points in elliptic curves over the presumed field, and the computation involves lots of division in the field, so lots of calls to Eglandine algorithms, so it increases the chance to find non-trivial factor of n. Currently, these algorithms still the best algorithms for divisors nodes exceeding 15 to 16 digits. Its running time is dominated by the size of the smallest factor p, rather than by the size of the running number n to be factored. The point of this algorithm is it has simple structures and low memory usages. It's the fastest running algorithm for all smallest-based algorithms, but it also has some cons. It's only suited for divisors not exceeding 15 to 16 digits. Due to these drawbacks, researchers found other algorithms to deal with it. In the next few slides, we will introduce those algorithms.
Different from the algorithm based on smooth, more excellent algorithms based on the idea of combining congruence to find integers x and y that satisfies square of y equals to square of x mod n. I will introduce quadratic sieve algorithm. The problem is that it is difficult to find x and y. The key step of QS is to use primary numbers in a factor base to filter quadratic function values in a certain interval. Here is an example. We find 6 equations that only include those 6 primary numbers. By solving the metric, we could find a linear solution and finally calculating p and q. If failed, we will choose another m equation to do the previous steps again until finding p and q. QS is the most effective method in the 1980s and in the early 1990s, and effectively worked on 50 to 100 decimal integers. It has successfully decomposed a double primary with a decimal digit greater than 129, even though the computing is so huge. One advantage of QS is that it is good for parallel computing, which means we can choose different m interval and calculus on different nodes. That will be efficient and more possible to find the result. However, it needs high memory requirements, especially in generating large-scale spreads metric. But till now, QS is still the most successful attack method for RSA in medium-sized composed number.
Here, I will introduce another algorithm, general number field sieve. Compared to QS, it can factor very large integers, but it needs additional setup steps, not as straightforward as QS. But for large composite number, the time for setup steps is still negligible compared to the time to factor the number. Basically, GNFS shares the same idea with QS. It also tries to find the perfect square difference to factor n. For example, if we can find a perfect square difference that is divisible by n, then we have around 60% chance to factor n. We can construct a possible table to calculate GCD between n as plus r, GCD between n as minus r. The implementation of QS is straightforward to find the perfect square difference, but for GNFS, the process is more complicated. The question is, how do we find the perfect square? Let's say if we already have a set of numbers and their prime factor set. Each number can be written as prime factor exponent notation. We can create an exponent matrix based on that. For a perfect square, the sum of all exponents must be divisible by 2. It's equivalent to find a vector A solving the equation. Basically, GFS is a fast algorithm to factor large number. It's a general algorithm that can be used to any number. However, it consumes a lot of memory due to the massive matrix operation. It's also a complex algorithm that needs additional setups. In summary, we introduced ECM, QS, and GNFS. Based on complexity, we can say GNFS is faster than QS and ECM, while QS is faster than ECM. In current applications, ECM can factor at most 7 9-digit number, while QS can factor at most 1 to 9-digit number. The latest record for GNFS is the factorizing of 2 3 2-digit number.
Previous methods are classical algorithms that have been fully tested and accomplished, so let me introduce this Shor's algorithm. It's based on quantum computing and is believed that it can solve RSA problem in polynomial time. And the idea is very simple. We find a non-trivial period r of this function a to the power of x. If r is an even number, we can factorize this function into these two parts, and each part contains a factor of n. So how do we find this r? We use quantum computing. In classical computing, each bit can be one state is either 0 or 1, but in quantum computing it can be both. It's called a superposition. So look at this superposition. It's both 1 and 0. If we measure it, we have a random outcome that is either 0 or 1 according to the probability. So n qubits can be 2 to the power of n states. Thus, manipulating this n qubits is just like manipulating 2 to the power of n classical bits. Thus, this can be very fast to compute R. Theoretically, the time complexity to compute R is O log R. But quantum coherence can be easily affected by environment, which is called quantum decoherence, and some methods are proposed to deal with this problem to solve the information lost in quantum computing, but they are mostly too costly. Compared to classical algorithm, this Shor's algorithm is very fast, of course theoretically, and it contains a lot of potential because of quantum computing, but it's very hard to build quantum gates, so it only exists in laboratories and simulations, and it contains a lot of errors, and it's pretty hard to handle with them. Overall, it is not yet practical, thus there is no application scenario right now, but we believe that it is worth looking for.